take this off. It's my great pleasure to introduce Harrison Tran, who is giving his master's presentation today. Harrison came to us from Cornell just 2 years ago, so he's finishing up in a fairly unusual 2 years. Shortly after he arrived here, he helped me wrap up a paper that I'd already been kind of fiddling with for a couple of years. And we got that knocked out and published in GRL in pretty short order. And then he went on to do a first authored paper that he's working on and is really on the verge of being submitted right now, so that's fantastic as well. And we're looking forward to seeing that come out, and that's also the core of his MS thesis. And in the process of just the 2 short years he's been here, he won the Bretherton Best Poster Prize at the previous poster session. I believe that was, is that right?
Yeah.
And he also won a Best Student Poster award at a national or international conference, the International Precipitation Symposium, right? So he's already gotten a couple of accolades for his work in those 2 very different settings. So today he'll be talking about reconstructing precipitation occurrence and specifically trends in precipitation occurrence over the global oceans over a 7-decade period. And take it away.
All right, before I begin, can everyone in the back hear me very well from back there? All right. So thank you, Dr. Petty, for the great introduction. So as you heard, I'm Harrison. I'm a master's student in the department. Just a year and a half in, it's been a wonderful time here at AOS. And I'll be talking about trying to develop a climatology of oceanic precipitation from a pretty long period of record, 1950 to 2019, using shipboard observations. So before we get into the details of this, here's just a general outline of what we'll be covering today. Of course, just starting talking about oceanic precipitation in general, why it's important in our current understanding of oceanic precipitation, where it comes from, and the like. Then we'll talk about, specifically as it pertains to this, my thesis, just what's the history of shipboard observations, what role do they play in our understanding of climate, and how have ship observations been used, and specifically, with regard to precipitation, how they can help us figure out more about precipitation than what we usually use for our current data sets. Then we'll get into my research, so talking about the data sets that are used in this project and the methodology that we use to try to reconstruct and figure out what's going on from the ship data, and then present the results and some key takeaways from those findings, and then hopefully there's going to be plenty of time after that for questions and comments. So I'd like to start out with this quote, not a well-known quote, it's kind of buried in a journal article in the Royal Meteorological Society quarterly journal back in the early 1900s, but it really encapsulates just sort of the idea of how difficult it is to measure and to sample oceanic precipitation. So as you see here from Sir David Wilson Barker, who was president of the Royal Meteorological Society in 1904, the question of the rainfall, or I guess any precipitation in general, is perhaps the most unsatisfactory with which to deal with in ocean meteorology. And specifically in this case, he was talking about how difficult it was to use rain gauges over the oceans. And that's because when you try to put a rain gauge on a ship and try to measure the rainfall, there's going to be a lot of effects from the ship being in motion. There's wind deflecting around the ship, around the rain gauge, that makes it difficult to measure. There's interference from sea spray and all of that. So historically, and still today, it's been very difficult to measure precipitation over the ocean, which is unfortunate because oceans play such a pivotal role in our global climate and with precipitation. Now, I probably don't have to convince you how important precipitation is to global climate. It's obviously a very massive part of our daily lives and affects everything from ecosystems to civilization in many facets, either that's agriculture or sort of water resources for various facets of life. But oceans receive 77% of the global precipitation, so the vast majority, as you might expect, given the global coverage of the ocean. And annually, just considering the flux of water from the atmosphere to the ocean, that you can see there on the bottom left, that figure from the IPCC 6th assessment report, ocean precipitation is pretty much the second largest flux of water between any of these land, air, and ocean sources and sinks. So that's, you can see the figure there, 424,000 kilometers cubed of water is transported via oceanic precipitation. So you can tell this is a pretty fundamental aspect of the climate that, if we can nail this down, explains large fraction of our understanding of global climate. And obviously there with evaporation and precipitation being a fundamental part of phase changes and the oceanic and atmospheric energy budget, if we can understand precipitation and measure it adequately over the oceans, that can go a long way into our understanding of the global energy budget, which then goes into understanding how climate change will operate and sort of how that manifests in terms of precipitation and other features of the climate. But despite how important oceanic precipitation is, or I'll go into that later, it's not very well sampled. Though we do have some sort of understanding of sort of what we'd expect from climate change in a warming climate, based largely either on physical, thermodynamic considerations, or climate models. So generally, as one might expect from the Clausius-Clapeyron equation, as the water holding capacity of air increases with higher temperatures, we may see an increase in general in the average global precipitation amounts, with in general, precipitation distributions tending towards more heavier rainfalls. So you get events with just more extreme amounts of precipitation. And generally, a lot of this is encapsulated in the idea of this sort of paradigm called wet get wetter, dry get drier. In general, more humid regions will become more humid. Soil moisture increases for those regions, while drier regions tend to get drier. And this is, you can see this is pretty true, at least in the modeling over the ocean. You can see in the figure there. Generally, in the dry subtropical areas over the oceans, that's where we'd expect to see drying. You can really see the intertropical convergence zone there, moistening up. In this particular simulation, I believe this would be the RCP 8.5 from CMIP 6 models. And in general, of course, as you might expect with a warming climate, the sort of polar areas, especially in the Arctic, the areas that are receiving frozen precipitation at some point in the year, that area is expected to decrease. Now, of course, there's a lot more in precipitation you can sort of describe aside from just the phase or the intensity, the quantitative amount of that precipitation, but a lot of that comes down to factors that are pretty uncertain in climate science. Of course, aerosols and clouds play a large role sort of in the microphysical processes of what drives certain types of precipitation. And you can ask any climate scientist, they'll tell you that aerosols and clouds are one of the hardest things to nail down in climate science. But despite how important all this oceanic precipitation is, in-situ coverage is poor, and poor might be a pretty generous way of putting it. Obviously, you can't really put a rain gauge and stick it in the middle of the ocean except for very few specialized buoys with specialized gauges. But as you can see there, sparse to non-existent coverage of any sort of in-situ measurement of precipitation, aside from those buoys, maybe a few specialized vessels. You might have heard of the Ocean Rain Project, which had some ships going around the global ocean with some specialized disdrometers to measure precipitation, but those are just a few ships out of the many. And then sort of assuming that some observations from islands and atolls are going to be representative of some surrounding area of the ocean. So New et al. In 2001 did a little bit of an analysis of our coverage of rain gauges, basically trying to estimate what percentage of the Earth's surface is, I guess, representative of, or would gauges be representative of. And they estimated about 25 to 35%, which is pretty bad. And it's even worse if you consider, okay, Earth's land surface is about 30%, so we're pretty much not even covering anything in the ocean from rain gauges. And Kidd et al. In 2017 estimated only about 4% of the ocean was within 100 kilometers of a rain gauge. So we're really just not seeing anything at all using rain gauges. So how do we even know anything about oceanic precipitation to begin with? Now, a lot of our current understanding of oceanic precipitation is based on satellites and remote sensing. So this is really the backbone of our current understanding of precipitation. So this is just a little history, just a little backgrounder on the satellites that are involved. So generally, since the 1970s up to the present, it's been a sort of progression from using early methods in the visible and infrared spectrum, just looking at cloud top temperatures and seeing if you can estimate the rainfall just based on cloud brightnesses. But pretty revolutionary changes to the satellite-based record happened in the 1980s, the launch of the Special Sensor Microwave Imager, SSMI, in 1987, which brought passive microwave observations into the fold for estimating rainfall. And foundational paper was written by Thomas Volheit that allowed the estimation, especially over the ocean, using the brightness temperatures and the effects of rain on brightness temperatures to estimate precipitation. And then sort of the modern era has been defined largely by the use of active microwave sensors. So that's actually putting radars in space and estimating rainfall that way, much as we would from land-based radars. But all of these methods are still in play, even though there's been an evolution towards these more sophisticated sensors. We still use passive microwave, and we still use a lot of visible and infrared methods to estimate precipitation. And all of these together are used to form sort of our global climatology of precipitation dating back to the 1970s. You can see an example of that from the GPCP, which is one such database or one such climatology of precipitation that uses these satellites and attempts to sort of merge the estimates that you would obtain from each of these satellites into a global climatology.
Quick correction on the date there for trim DPR, that would be 1997.
Oh, sorry, yeah, 1997 for trim DPR. And DPR would be just the instrument for the radar instrument on trim. But, I mean, satellites have been just fundamental to our understanding of oceanic precipitation. But, you know, satellites are not perfect at what they're doing. You can imagine if we have plenty of difficulties estimating land-based precipitation using radars, you can imagine all the radar to precipitation amount, sort of empirical formula that have been devised for that sort of thing. You can imagine that same sort of difficulty is in play for space-based radars, and there's even more uncertainty with that, given how limited our coverage often is. So one of the biggest difficulties with satellite precipitation is they often have a hard time capturing light or shallow precipitation, and that's often characteristic of what goes on in the higher latitudes when you have a lot of stratiform precipitation, a lot of drizzle and light, either rain or snow. That often is pretty difficult to pick up on even on a lot of our passive microwave sensors especially. And those methods and any sort of method that resides on the cloud top aren't going to really capture the low-level characteristics. What you're seeing for the brightness temperature is really the impact of the bulk characteristics of a cloud. So oftentimes you might not be capturing what's really actually going on in the surface. And while the period of record is sort of long, that GPCP product I mentioned earlier goes back to 1979. The more reliable satellite estimation methods, especially with passive microwave, that emerged only in the late 80s. So our period of record is relatively short, especially for any sort of climate applications. And at the end of the day, these are indirect methods of obtaining precipitation. And of course, ideally, we want to have some sort of in-situ method for obtaining that. So as I mentioned earlier, we have a pretty limited view with gauges over the oceans. But one thing that can help us is ships. And there are certainly a lot of ships out there that can report meteorological information. So I just want to talk about sort of the history of ship observations, because it's pretty fascinating. Obviously, with maritime, the maritime importance or weather plays a large role in ship traffic and where ships go, and it's been a fundamental importance of weather to maritime and commercial interests. So there's been a long tradition of cataloging oceanic weather from these ships. That's dating back to at least the 17th century. There's plenty of logbooks from that era just documenting the weather conditions pretty routinely. And the first coded systems were actually systematically logging the weather emerged in the 1800s. You can see an example from this one. This is actually from 1906, but it uses a method devised by Sir Francis Beaufort of Beaufort scale fame to kind of codify the weather there and report it in a systematic method for commercial interests. And especially after the 1853 International Maritime Conference in Brussels, there was a pretty big effort to unify a database where you could pull together all of these observations of oceanic weather. And that really took off after the 1850s. So ships, since buoys and specialized vessels only emerged later in the 1900s, for a pretty long period of time, our only form of in-situ precipitation for essentially almost the entire ocean is going to come from just ships reporting these observations. So still today, ships are reporting weather conditions throughout the world pretty routinely. And today they're defined by the WMO Manual of Codes, which prescribes the current conventions for how weather is reported from ships. And a lot of the conventions that are used by the World Meteorological Organization actually came about earlier on in 1929 with the International Meteorological Conference in Copenhagen, which set a lot of the standards and standardized codes for reporting the weather. A lot of the ships today that do report, so not every ship reports the weather, but those that do tend to fall under what the program called the voluntary observing ships. So these are fleets of ships that are actually designated to report weather at fairly routine intervals under the WMO permission, you can see there. So these ships and the crews on these ships are actually trained by their respective national meteorological and hydrological services to provide these routine reports. And a lot of these are automated, but oftentimes, especially for something like reporting the weather conditions, they actually have a weather observer on board trained to report the weather at these intervals. And these are communicated either via satellite or radio back to those national meteorological services, and then those go into sort of large compendiums of just oceanic weather. So that includes things like temperature, pressure, in addition to present weather conditions. So this is a little animation that Grant Petty put together. I'll just play this for a little bit, not the whole thing. But you can see each of the blue dots in this. So this is stepping month by month from 1950 to 2019. Each of those blue dots you see there is a ship observation specifically for the current weather condition. So either it's raining or it's sunny or that sort of thing. And you can see there's a lot of data to work with in this map. Obviously, there's going to be a lot of sort of areas, especially in Southern Ocean or maybe in Southeastern Pacific, where there's a deficit of ship observations. But there's plenty of coverage that buoys aren't going to see a lot of these areas, especially closer to the North Pacific and the higher latitudes. So it's pretty helpful that we have all these ships traversing much of the globe. And if we can extract some information from those ships, that would be tremendously valuable on science. But of course, like satellites, ships are obviously not going to be perfect observation platforms. And if you just imagine how ships observe the weather, you can probably come up with a lot of sort of different ways that they might be susceptible to different biases. So for example, you'll often see in the literature talking about ship observations that they may be subject to a fair weather bias or a foul weather bias. So in the first case, maybe you have ships that might, especially a smaller ship that might divert towards calmer conditions, and they, as a result, might report more calmer or fairer conditions. And the foul weather bias is if they are moving through sort of inclement conditions, then they might slow down and tend to report those conditions for longer. In addition, especially with just reporting what the weather conditions are like, especially when it comes to precipitation intensity, for example, there might be there's going to be a lot of subjective interpretation to that, determining whether something is light or heavy, drizzling, non-drizzling, showery or not showery. There might be some differences between weather observers, so a lot of that comes down to subjective interpretation. And of course, ships are constantly moving, and they're pretty sparse compared to land-based observations, so there's going to be some, you're going to have to work with, especially binning data, if you're going to try to look at ship observations as a whole. Now, a lot of these weaknesses are weaknesses you can imagine with ship observations, and they often appear in the literature. But from what I've seen, a lot of it tends to be pretty speculative. It's hard to quantify exactly what these biases are. But some attempts have been made to quantify biases for ship observations in terms of, say, wind or wave heights and that sort of thing. And so far, it's been pretty inconclusive whether they're actually biased in a certain way, or in general, we can sort of use them in aggregate to describe weather conditions fairly reasonably. And just one example of that, Ellis et al. In 2009 reported that at least using the CloudSat satellite, the ship observed frequency of precipitation was pretty consistent with satellite observations. So, as I mentioned, ship observations have been used fairly often for a lot of different parameters, actually, and they've been pretty valuable, especially for that first element, sea surface temperature. So you can imagine a lot of sea surface temperature data sets, especially those that go before, say, the 1950s or so. They're going to take a lot of their sea surface temperatures from ship data, because that's really all we have over much of the ocean. But that image on the right there is an example of a paper that uses sea fog observations from these ships to build a climatology of fog. Then there's been other fields that ship observations have been pretty valuable for. But what we're going to be keying on for today is specifically one aspect of what gets reported from ships, and that's the present weather code, which is often abbreviated as WW. So, as I mentioned earlier, it's been long recognized that quantitative precipitation measurement is difficult. That quote from the beginning in the early 1900s was specifically addressing this problem, that you can't really just stick a rain gauge on a ship and expect to measure the amount of precipitation with any accuracy whatsoever. So instead, what we're keying on for this research is specifically the qualitative reporting of weather phenomena. And so the WMO Manual of Codes, which I described earlier, prescribes a sort of numbering system for describing what the weather conditions are like. And there's 99 different sorts of weather phenomena that a weather observer can report as being just the state of the weather at that time. So there's 99 values. The first 50 are related to just the current state of weather in the absence of current precipitation. But key for this research is the values above 50, which describe various sorts of precipitation. And they're roughly categorized into these categories. You can see 50-59 as drizzle, got rain, frozen precipitation, showers, and thunderstorms. And each individual code is going to have a slightly different character. Maybe there's heavy precipitation or heavy rainfall. There may be a different frequency of that precipitation. Maybe it's intermittent or continuous, or there's snowflakes or ice pellets. And so each code is going to describe a slightly different weather phenomena that's ongoing. So especially in the 1960s and through the 1990s, there was a lot of, since ships were really much all we had, and satellite observations at the time were fairly unreliable, we often use these ship observations, especially these present weather reports, to try to get some quantitative understanding of what was going on over the oceans. So pretty foundational papers were Tucker in 1961 and Reed in 1979. These looked at these present weather codes and compared them to the weather reports that were coming from land observations, which did have the benefit of having rain gauges, and using those sort of two different data sets to calibrate and estimate precipitation amounts from ships. So for example, you can see here from Tucker 1961 using some specialized ocean weather ships that were over the North Atlantic and using land observations from Britain to estimate just some idea of the annual rainfall amount over the North Atlantic, because that's really all we had at the time. So with all that in mind and motivation in place, here are some key questions that I'm hoping to answer in the course of this research. So just generally, since the 1990s, we've mostly focused on satellite precipitation, and ship reporting has kind of fallen in the wayside in the literature as far as estimating precipitation, but they are still our only in-situ source of oceanic rainfall for much of the ocean. So the idea here is, even using a long period of record from 1950 to 2019, do we continue to see physically sensible data that we can extract from these ship observations? And key questions for this research are, has oceanic precipitation changed since 1950? And if so, what are the distributions of the changes, which we'll be focusing on today? And the overall goal of this project, which is sort of a future goal, is can we reconstruct quantitative estimates of the actual rainfall amounts using information from before the satellite era, while using the benefit of satellites today to calibrate those results, as Tucker in 1961 did with land-based observations. But for now, we'll be looking at just mostly focusing on precipitation frequency, since that quantitative precipitation amount is more of a future goal. So looking at these present weather reports, we're going to be estimating, just in general, if I'm referring to frequency in this case, we're talking about the fractional time precipitating. So in this case, for example, what percentage of the time is it raining? And that's going to be sort of our key quantity that we'll be examining in this research. So moving into the data set that we're using, this is the key one here, International Comprehensive Ocean Atmospheric Data Set, or International COADS. This is just a really large database of maritime observations dating all the way back from 1662 to the present. It's a really long period of record of a whole bunch of ship observations from pretty much the global ocean. And so this effort began in 1981 as a joint effort between the NOAA and NCAR to really pull together these observations. And over the years, we've sort of uncovered more and more data sets, ship logs, mariners logs, and that sort of thing, more and more observations have been added to this data set. So this data set includes everything from ships, buoys, floats, oil platforms, any sort of maritime platform is included in this data set. It's a really robust, really rich data set, and has been frequently used for sea surface temperatures, winds, and other marine phenomena as well. And so, at least programmatically, this data set also adopts the WML conventions, including present weather. So we'll be keying on that quantity as we analyze this data set. So specifically from this data set, although it goes back to 1662, the focus of this research is from 1950 to the present. So that's after the standardization from the World Meteorological Organization, and that's going to be after World War II. So we're hoping that at least in this period of record, that we're going to see a little bit more consistency after the wartime. And specifically, there's a lot of different marine platforms included as part of this data set, but we wanted to look specifically at observations that we could use to build a long, consistent period of record. Of course, things like Argo floats and buoys are going to be more recent, so we specifically wanted to look at what kinds of observations sort of had the longest period of record specifically within this data set. And so that's human observed conditions, so not automated, human observed conditions on conventional ships. There are some other ships like light ships or ocean weather ships which mostly stay around one area, and so we wanted to, but those are going to provide pretty, or sort of heterogeneities to the data set since they're only in one place and are in a pretty limited location. So specifically, we're just using any sort of conventional ships. That includes both commercial ships, merchant vessels, and any ships that are similar to that. But to filter this data, there were some other exclusions that we had to make. Two particular sort of sets of data within this category of ships kind of provided a lot of inhomogeneity. Specifically, they often reported just fair conditions, almost seemingly automatically, without much regard for specifically clarifying what conditions were going on. And those are these two data sets you can see here. Also within this data set were a bunch of low latitude or high temperature frozen precipitation reports, which are clearly erroneous. So in order to sort of remove some of those, we only looked at observations that had an accompanying air temperature report, so we could filter out any low latitude or possibly erroneous reports.
Yep, the chances of hail.
Or sometimes it was hail, but specifically in this case, because hail is actually a category within this data set, but specifically this is like things like snowfall. That's coded separately from ice pellets or hail. But these were pretty unreasonably high temperatures for snowfall. So here's just a look at the data set once past filtering. So even those, after we're filtering those ships out, we still get a really large data set that we're able to work with for the 70-year period. So that's 99.7 million observations. So that's roughly about 1,000 observations every 6 hours every day since the 1950s to the present globally. And you can see a map of, this is a 1 by 1 degree grid of where we're getting these ship observations from. There's a lot of clustering around ship tracks you can see there, but at least, especially in the Northern Hemisphere, we get pretty good coverage of just ship observations, and we can probably make some sense of what's going on quantitatively. And it's been pretty consistent from 1950 to 2020. It technically peaked with a number of observations in the 1980s, but generally in the ballpark, at least logarithmically, we're getting pretty consistent amounts of reporting, both year to year and within each year, a fairly good amount of reports for each season. So we're getting pretty consistent observations over the ocean year-round from these ships. And just a little bit as an aside, this is a minor part of this research, but I did some correlations between what ships were observing and the SST. So this is just a little overview of the 2 SST data sets that I used. And I used 2 just because I wanted to see if these relationships held up between different data sets with different data sources and different resolutions. So we used the the NOAA ERSST, which is at a 2x2 degree resolution, and the UK Met Office's Kaplan Extended SST, which is at a 5x5 degree resolution. So to estimate frequencies, one thing you could do is just simply take like a global grid of the ocean, bin ship observations into each little box, and then for each grid cell, you can estimate that if, for example, we're seeing 10 observations of rainfall out of 50 total observations in that grid box, then it's raining about 10% of the time. But this can provide pretty inconsistent results, especially for phenomena that are rare or in locations that aren't very frequently observed. You can often just guess that something is happening 0% of the time, especially if we're looking at a finer resolution, simply because something is just not being observed very frequently. And so that was pretty undesirable for this research. So what we did instead to estimate frequency was we took a sort of Bayesian approach, and we said that if we're observing some sort of phenomena, however many, maybe m amount of times, or we're estimating a sort of frequency, what's the likelihood that that frequency is resulting from the true frequency being some sort of value between 0 and 1. And when we do that, we get a pretty similar value to what we might expect from just that expected frequency. So if we have m observations of some phenomenon and n total reports, there's an estimated frequency in f hat, which is pretty close to f, but especially for areas that aren't observed as frequently over the open ocean, this is a pretty useful estimator that doesn't just constantly converge to 0 for infrequent phenomena. And then we can also provide an estimated error on that estimation of the frequency. And this, at least formulation here, is kind of, you can think of it as a root mean squared estimator. Given sort of all possible frequencies, what's the estimated error of certain f hat? So what we did to provide a global map of oceanic precipitation was we binned our ship observations into various global grids with various resolutions, the finest one being a 1x1 degree resolution, up to 13 by 26 degree resolution. And if we sort of do all these calculations in that way, we obtain sort of an estimated frequency and an estimated error for each season and each year. So the goal of this is when you have all these maps of global precipitation at these various grids, they all have that associated error estimate. So what we did was our goal was to get to a 1x1 degree grid of global precipitation. But of course, in some areas, you'll have a lot of observations within that 1x1 degree grid, so you're more confident in your estimate of precipitation there. But in other areas that are more sparsely observed, we want to sort of pull in observations from around that surrounding area to estimate that precipitation within that grid cell. So actually, we do obtain a 1x1 degree grid cell in the end, but what actually happens is that the value that we obtain for more frequently traversed areas, that's going to be reflective of the observations specifically in that grid cell. And then for more sparsely observed areas, the value that we obtain on that 1x1 degree grid cell is going to incorporate sort of an aerial average of the surrounding area. So you see there, that's sort of a goal for obtaining kind of a smooth map of precipitation globally. And then once we have these frequencies and estimates, then we can start computing trends, changes, and correlations between the pre-satellite era to the current satellite era, and estimate 70-year trends. So we just use the ordinary least squares regression. And so when I pull up trend maps, you'll be seeing just a decadal trend of precipitation frequency of the ocean. And for all of these estimations, statistical significance test was applied at the 95% confidence level. So with that, let's get to the results. And this is some pretty interesting stuff. But before I get into specifically what I did for my thesis, it would be remiss of me to not mention some of the earlier work that Grant Petty was mentioning earlier. So at first we were looking at just overall precipitation. So instead of looking at a specific class of precipitation, just how often are ships reporting that it's raining or snowing or any sort of precipitation versus when it's not. You would assume that's a pretty easy determinant for a weather observer. So this is kind of the most conservative estimate of just how precipitation is changing. And in general, you do get a pretty good, reasonable map of precipitation just based on these ship observations alone. You can see the IPCZ there, South Pacific Convergence Zone, and the sort of stratiform precipitation that predominates in the higher latitudes. And interesting, you'll notice in the frequency map is that there's an increasing trend in frequency of precipitation over the tropics and the subtropics, and there tends to be a decreasing trend in the higher latitudes. And for many of these areas, we're seeing these statistically significant trends over the 70-year period. But for my research specifically, I was looking at 4 different sort of classes or groupings of precipitation, and these are adopted from work that Grant Petty did in 1995. So these tackled sort of different slices of precipitation, because obviously there's many different kinds of precipitation, and we often can observe, or we can't really distinguish between a lot of these different types of satellites alone. So these really get to the problem of are we seeing sort of trends in these phenomena that might not be as well captured by satellites, or we can extract some information about how precipitation character of the ocean is changing. So specifically, we'll be looking at drizzle as a fraction of all precipitation, moderate or heavy intensity precipitation as a fraction of non-drizzling precip, any precip associated with thunderstorms and deep convection as a fraction of non-drizzling precip, and then frozen phase precipitation as a fraction of all precip from these ships. So we'll start out with drizzle. And you can see that we obtain results that are pretty consistent with what we understand about drizzle. Drizzle is fairly common in the subtropics. You can see in the coast of southwestern Africa, up there in the northern Pacific, and off the western coast of Peru and Chile there, the annual map there. And you would expect that drizzle is fairly common with marine stratiform clouds, and that's where they're predominantly located. So that's consistent with what we'd expect. So it's a good start when we're getting results from sort of these disparate ship reports that are actually consistent with what we might assume just as a prior. And along with that point with marine stratiform clouds, we do get zonally contrasting correlations of how frequently it's drizzling with the sea surface temperature anomaly. And especially in these marine stratiform rich areas, for example, off the equatorial Pacific here, or off the western coast of the United States and Mexico, we get a negative correlation between drizzle frequency and SST, and that might be related to warmer SSTs, or that may be related to cooler SSTs causing increased stability, and you'll see more frequent marine stratiform clouds in those cases. But here are some changes that we're observing with drizzle, at least in the ship record. Especially a point here, if this is the zonal mean frequency of drizzle, you'll especially notice that in tropics, there's a sort of increase in drizzle from the pre-satellite era before 1979 to the satellite era from these ship observations. So you'll see this on the map on the next slide, but it does appear to be some sort of increase in drizzle frequency in the tropics, and then a decrease, statistically significant decrease in drizzle frequency in the Northern Hemisphere mid-latitudes. And that's especially apparent here in this map this is the relative trend in percent per decade. So this is the fractional increase of drizzle frequency, and you can see especially a lot of the tropics, we're seeing a statistically significant increase, and then the statistically significant decreases are less spatially apparent, but we do see that, especially in the areas where there are frequent stratiform precipitation, you'll see it in some of the seasonal maps as well, that there is a decrease in the drizzle frequency for those areas. And for some areas, for example, the Brazilian East Coast, some of that trend, at least the magnitude of that trend, there's some potentially erroneous inputs from just a few years, but there is a gradual increase there. But a lot of other areas have pretty consistent trends over the 70-year period from the pre-satellite era to the present era. So while the focus of this research wasn't on the dynamical explanations for why this might be occurring, I did look at just possible explanations for why we might be seeing stratiform clouds produce less drizzle, and there might be a role of aerosols in that. Aerosols would drive down would increase the amount of cloud condensation nuclei and push towards sort of smaller cloud droplets for marine stratiform clouds that might reduce their propensity to produce drizzle, and maybe for some other clouds that might increase their propensity to produce drizzle by decreasing sort of the cloud droplet size or precipitation size. And there might be some other influences. For example, you'll notice here that there might be vaguely some sort of multi-decadal signal in the drizzle frequency that's occurring in the Indian Ocean and in the Western Pacific. And this actually kind of follows the Pacific decadal oscillation time series. There might be some broader teleconnection influence on drizzle production, which is pretty fascinating to see this play out.
Just one point of elaboration. I believe the thinner curves are the seasonal results, right?
Yeah, the thinner curves are the seasonal results. They're labeled up here. For each of these slides, we do see this graphic. That's a legend there. The bold line there is the annual frequency.
Yeah, the reason why I was actually very pleasantly surprised as I didn't really expect it, that there's a lot of coherence across seasons. So if you look at the curves, you're seeing the same effect in all seasons that are more or less consistent with the annual trend, which you wouldn't expect if we were looking at random noise. So,
Except the North Atlantic.
Well-
There's a big departure between the average and the other 3 seasons and the summer in the North Atlantic, which is interesting.
well, that's the magnitude, right? But
Yeah, the trend's
shape-
the same, but
The trend is similar. So the shape of the curve may vary because you get more drizzle in the wintertime probably, or whenever in North Atlantic, maybe the other way around. But anyway, the magnitudes can change, but the shapes of the curves tend to follow each other pretty well, which suggests it's a real signal and not just random noise.
Yeah.
So that kind of temporal coherence is kind of reassuring that there's something to this. And we also see spatial coherence, which that'll show up later. But that's one thing that made me think that maybe we're onto something here.
And so the IPCC report talks about a reduction in marine boundary layer stratiform clouds, right? So that's what we expect with the future?
Or at least if we're making the assumption that as the oceans warm, that will decrease the stability, so you would maybe expect less marine boundary clouds. I don't know if we've seen.
I think the IPCC has some summary statements about that being the expectation.
Yeah, though I'm aware that that is the expectation. I'm not sure if that's shown up in sort of the cloud climatology, or at least in the historical record, if we actually have seen that decrease materialize.
Oh, you mean you're not sure if you're seeing it here?
Yeah, all right, because I know at least in model projections, they are predicting a decrease in marine stratiform clouds, but I don't know if between 1950 and 2020, for example, that has actually been observed by satellites. So this
Well,
could,
I don't think it's been observed by satellites,
Yeah.
but that's what you're seeing,
yeah,
right?
or I'm just suggesting that there might be some influence of, that might be playing a role in this, at least in some localized capacity.
I see, okay.
So then looking at our next category, now we're just looking at moderate and heavy precipitation. As one might expect, you can see a lot of more heavier precipitation in the lower latitudes, but this includes all phases, so we also see heavier sort of snowfall or frozen precipitation in the high latitudes as well there. One thing that's interesting that we're seeing here is that there seems to be some sort of inverted pattern in the relationship between heavier precipitation and SSTs between the northern and southern hemisphere. We get pretty strong negative correlations between SST and heavier precipitation in the subtropics in the northern hemisphere, but in the southern hemisphere, at least where we're getting statistically significant results, we're seeing less of that sort of configuration there in the southern hemisphere. When we look at trends in the ship data, one thing that sticks out, you'll see in this trend map, is this belt of this positive trend since the 1950s in heavier precipitation over the subtropical Central Pacific, as well as increases in the Mediterranean and in the Yellow Sea and some other pockets in the northern hemisphere there. And you can also see that in this map, this is comparing the composite frequency before the satellite era and then during the satellite era, the differences between the two. And we're seeing those same regions highlighted there, especially that belt in the sort of Central Pacific there in the subtropical latitudes. So one possible mechanism that could explain this, now for some areas, there might be, this could be a little bit of a suspect increase in the sort of frequency of this precipitation. Not really sure exactly what might be the cause of this sort of more sudden increase, but in other regions it's a little more gradual, especially in the Central North Pacific. At least one mechanism that could explain why there's an increase in this frequency of heavier precipitation is if we're expecting, as with climate models, that the northern Hadley cell would be expanding and the tropical belt would be widening, one might expect that sort of the area of heavier precipitation is going to expand northward, maybe kick the area of subsidence, subtropical subsidence to the north, so maybe we're expecting, or maybe that could be a reason for why we're seeing heavier precipitation in the Central Pacific for ships. Less frequently observed, of course, from ships is thunderstorms and deep convection. So in this case, when we're saying deep convection, this is more of just within the present weather code, anything that might be sort of the heaviest precipitation that we're seeing there. And generally, we're actually seeing results from ships that are consistent with global lightning sensors, at least within the more modern period of record. But you can notice that there's more thunderstorms and deep convection around, did we say, West Africa, around the Gulf of Mexico, in the Mediterranean, and especially in the equatorial Indian Ocean. You can see here during the winter months, so that might be related to the monsoon there. And then with SSTs, a similar relationship between correlations between the frequency of thunderstorms and deep convection and thunderstorm activity, mostly over the subtropics, and then like an inverted pattern over some limited area of the tropics off the East Pacific there. So when we look at trends, one thing that sort of sticks out here is especially in the North Atlantic, sort of in the subtropical North Atlantic and the higher latitudes there's been a decrease in thunderstorm frequency in all seasons and the annual amounts since the 1950s. So that's pretty interesting to see that bear out in the data. There's been a few areas of increasing trends, especially in the Mediterranean Sea and the Yellow Sea, as I pointed out earlier. You can tell there's some slight upwards tendency over the 70-year period of record.
Harrison?
Yep.
Is this category, do they have a separate category for tropical cyclones?
No.
Or this would be all
This would just be
combined
any,
with this?
I think specifically it's coded as if sort of precipitation accompanying either thunder or lightning within the previous hour.
So it doesn't distinguish
No.
TCs or not in this
Yeah,
case?
so this is just any sort of thunderstorm.
Thank you.
And at least as far as reanalysis data is concerned, where we are seeing some increases in thunderstorm activity, so again, the LC and Mediterranean Sea, that does line up at least with ERA 5, with maybe an increase in Cape within those areas. For example, you can see there positive increases, but less certain is sort of the trends that are apparent over the North Atlantic there. You can tell these darker shades are kind of are the result of, since thunderstorms are pretty infrequent over the North Atlantic, even the slightest bit of changes can be pretty dramatic if we're talking about the fractional tendencies there. But there is a pretty substantial decrease there. But as far as the mechanism for why that might be occurring so far, at least if we're just using this sort of metric alone, it isn't as apparent why there would be such a large decrease in thunderstorm activity over the North Atlantic. And then for the last category, looking at frozen precipitation, you can see pretty much as we might expect that frozen precipitation is going to be mostly above 35 degrees north and or 35 degrees north or maybe 35 degrees south and forward of those locations, with a tendency for more snowfall closer to continents on the western side of the oceanic basins there, and pretty strong negative correlation between how frequently we're observing frozen precipitation with SSTs. And pretty consistent with climate observations, we are seeing a sort of decrease, especially in the Northern Hemisphere. Along the fringes of where we expect to see frozen precipitation, there's been a decreasing trend in the frequency of frozen precipitation. But sort of one area that sticks out that is at least statistically significant is this sort of blob right here off just east of Newfoundland, where there's been an increase in frozen precipitation. And the interesting thing about that is that that's actually pretty closely co-located with what has been termed sort of the North Atlantic warming hole, which has been speculated due to the weakening of the Atlantic meridional overturning circulation, that this is one area pretty much while the rest of the global ocean has been warming for the last 50 years, this is actually one area that's been cooling. And it's interesting to see that line up with an increase in frozen precipitation there from ship observations.
Well, also, I'd like to mention that it still puzzles me a little bit that it makes sense that the blue stripe would show up in the North Pacific because you're retracting the area where the snow would be occurring because of warming. But why are we getting the increase up toward the north and the west?
I wonder if it's increased continental cold air coming off in the early part of the season. Because it looks like it's got a, well, maybe it's the middle of the season, December, January, February. Maybe it's cold air outbreaks over a slightly warmer ocean.
So more cold air outbreaks and
And
more
lake effect
convection.
snow, maybe. Yeah, I wonder if that's not part of it.
And I will note that even though it's not statistically significant here, but you can see sort of a a trend from decreasing frequency is maybe like southern Japan and southern Yellow Sea towards increasing trends over the Sea of Okhotsk and northern Japan. That's actually corroborated by land-based observations as well. We're seeing this sort of has latitudinal difference there in Japan.
Yeah, so maybe the freezing line is just inching poleward along the coast, and that's enough to make a difference in
Yep.
maybe the ocean effect snow.
And here's some regions of highlighted interest there. I've drawn a box mostly over these sort of transitional zones. And especially since the 1990s, there does seem to be some sort of decrease in those areas in terms of the frequency of frozen precipitation. One thing that is interesting is that these ship observations might be pretty sensitive to shorter term SST tendencies as well. So for example, I chose this area in North Atlantic, which in 2015 had a little bit of a kind of a marine heat wave there, the opposite of that, a cold blob in that region, unexpected cold blob in that region of the North Atlantic in 2015. And you can actually see that line up with this sort of uptick in, especially in the April-May season, in the frequency of frozen precipitation, which is actually higher than any previous year for that region. So it might be pretty sensitive to more localized and shorter-term SST changes. So with all those changes in mind for all those precipitation classes, just want to end up on some key takeaways from these findings. So what we're seeing is that these shipboard present weather reports are providing at least physically consistent results. We're not just seeing random aggregations of frequencies. We're actually seeing pretty geographically coherent and physically sensible results. Key takeaways from these precipitation classes specifically, we're seeing that increase in drizzle in the tropics and a decrease in drizzle for areas with abundant marine stratiform clouds. Tendency towards heavier precipitation in especially the subtropical Central Pacific, but as I pointed out, also the Mediterranean Sea and Yellow Sea, and maybe a diminishing sort of regression of the area of the Arctic receiving frozen precipitation, and maybe as the freezing line draws north. So a lot of these results are sort of summed up in a journal article that's awaiting review in JGR Atmospheres, but the ultimate goal of this whole entire project is now we have all these frequency estimates for different kinds of precipitation. Can we calibrate that with satellite retrieved precipitation amounts to actually map what we're seeing from satellites to ships, at least for the era from 1979 to the present, and then apply those sort of calibrations to before the satellite era to estimate precipitation amounts before satellites, so 1950s and the 1960s. But of course, the ship observation data provides a whole lot of different avenues for research. I mean, there's a lot you can do with this information. So you can talk about, maybe start looking at the dynamics of the microphysics of some precipitation changes, so for example, the increase in drizzle over the tropics and exploring that. You might even slice the data in some other ways, so I only looked at 4 different precipitation classes here, but you can also look at things like ice pellets or different kinds of snow or different intensities of snow and see how those have been changing for the last 70 years. And as well, looking at relationships between classes and other variables. So I looked at SST in this case, but for example, this is just something I plotted out really quickly, looking at transitional phase precipitation, so things like ice pellets or sleet, and how they relate to sea surface temperature, wet bulb temperature, or whatever other quantities that these ships are also measuring. So there's a lot you can do with that. And then lastly, one important role for ships is, of course, validations of climate model hindcasts, since ships are our only source of in-situ information over much of the ocean. And before I end here, just want to thank some people in particular. It's been a pretty tumultuous year, at least for me personally. So many here and beyond have helped a lot over the last year. So of course I want to shout out with my family, dad and mom, and my brothers Alan and Daniel for helping me and their generous support just throughout the years. And of course, all of you guys, vibrant AOS faculty and staff in the AOS community. It's been definitely a great 2 years here in Wisconsin. And specifically, I want to call out Quinn and Kaylin. Quinn, my office mate. Thanks for being a great office mate, and especially thank you for the couches, which were great source of relaxation over the past year. And Kaylin, who isn't able to be here today, but I want to shout out Kaylin for sort of entertaining me with this frequent conversations at lunch in the sort of graduate student lounge upstairs. And of course, I want to thank my teachers and meteorologists, on-air meteorologists from throughout the years. So they've been a big part of just why I'm here in the first place, and especially the on-air meteorologists from back home in Austin are what got me into this field in the first place. So wouldn't have been here without them. And of course, I want to thank my graduate committee, Dan Weimont and Hannah Zanowski, for both our meetings and of course probably reading my thesis right about now. And of course, last but not least, my advisor, Dr. Grant Petty. Thank you so much for giving me the opportunity to be here. It's been an honor being under your tutelage, and it's been
Likewise.
it's been a great, super great experience here. And with that, I'll head on over to questions.
I guess that.
I think the one really interesting aspect of this work is the human aspect, because everything you showed here, right, is based on those codes that are qualitative. That's correct?
Yeah.
I just want to make sure that I got that before I say anything stupid. So I have two thoughts. The first one is for that moderate heavy precipitation. I wonder if there's some sort of bias where if someone is spending more time going north to south and going into the tropics and back out of the tropics, if they'd be less likely to label something heavy precipitation farther north. And I wonder if you could potentially pull that out of the data that you have, whether or not you see that sort of thing specifically on north-south tracks versus east-west tracks. And then my second thought for your very low number of thunderstorms in the North Atlantic, I wonder if there is some sort of bias where at a certain point, once you have good weather prediction, if ships are just avoiding inclement weather, and then you wouldn't ever see that because you know that it's there, so you're avoiding it in the first place.
Yeah, at least to your first point, that is something that just thinking about the weather observers' experience with the weather, not even just the tracks by themselves, but just where they're from, just what their experience is with rainfall and that sort of thing, that could play a role. It's kind of hard to see that in the data. I mean, because at least for different ships, you're going to have different weather observers, and the ships are going to be taking different routes, so it's hard to really nail down at least, or try to bin ship tracks into certain classifications of if they're zonally oriented or radianal oriented.
Yeah.
That could be a bit difficult, but it is at least reassuring that as far as overall frequencies, that we're seeing distributions of intensities that are consistent with what we expect. We're not just seeing these random blobs of inconsistent results. So that at least is a bit reassuring. And then, sorry, your second question was about
Thunderstorms, I wonder
Yep.
if ships are avoiding them, and that's why you see decreased frequency.
maybe potentially for a smaller ship that would be able to avoid like a thunderstorm. 'Cause, I mean, thunderstorms are fairly smaller scale, localized things, so maybe a smaller ship might avoid it. But oftentimes for like a larger ship, if conditions permit, if they're going from point A to point B, and there's going to be some thunderstorm 5 days in, like they're not really going to worry too much about that. So I don't know exactly how much that sort of fair weather bias is going to play into that. I mentioned earlier that a lot of papers just mention a fair weather bias, but it does seem kind of speculative. And when we do actually try to figure out the biases in this data, we're getting pretty inconclusive results.
Yeah.
I'd actually like to add a little bit to your comment about the determination of like moderate heavy. That is, in fact, one of my largest sources of anxiety about this, because I was actually a weather observer on a ship for a couple of years and the land station for a couple more years. So it's very subjective. It's easy to go out and say it's precipitating or not precipitating. That's a very robust observation. It's easy to say whether it's frozen or liquid. It's easy to say if there's lightning and thunder occurring at the time of the observation, so that is fairly robust. But when you get to making the discrimination between drizzle and non-drizzle, and between light versus what is usually lumped together as moderate to heavy, that is subjective. There's guidelines that a lot of observers probably aren't even really fully aware of, and so it's very subjective. And I think it's a valid point that you have to worry about the degree to which observer training, observer experience, of where they spend most of their time. If you spend all your time in the high latitudes, you may be calling stuff moderate and heavy that nobody in the tropics would say is moderate or heavy. I don't know how to tease that out short of having rain gauges on the ships with the observers, in which case we'd have the information we want, right? But it's a valid point, and there's not really any good way that I know of to try to debug that problem. Yeah.
I wonder if co-locating your observations all the way back to 1950, you could use the NCEP reanalysis, or now the ERA5 back to 1940, co-locating in the North Atlantic with where are those observations relative to observed cyclones, or observed, quote unquote, in the reanalysis. Because if you started to see that there's a systematic bias to underreporting the intensity just forward to the warm front, you might say, oh yeah, people are not making a good statement about moderate versus heavy, vice versa. You might be able to tease some of that out that way.
Sounds like another project.
Yeah, I mean, it'd be a huge marriage of data sets, but you mentioned at the end, Harrison, the correlations you can do with other variables measured on the ship. Why not do them with other quote-unquote observations taken from somewhere else?
Yeah, absolutely.
Because that could be really cool.
Yeah.
And there's a lot of data to work with.
Yeah, that's neat. I mean, your whole thing is outstanding.
Great question in the back.
Sure.
Yeah.
That was very cool. Thank you so much. So in the last 6 months, in totally different fields, I have seen cases where the changing distribution of observations that are online caused trends to appear that weren't actually true trends, but were just because of the frequency of stations available. And some of these data sets have lots of observations. And I'm very curious what your thoughts are on that with this data set. Are there places where you should worry about the changing distribution or not having enough stations, and that just the changing frequency of observations is going to change the interpretation of trends?
Because I do think that, I guess with any data set, land or otherwise, that's going to be something to consider. But at least for just looking at the general trends and sort of where ships are reporting data and how often they are, we haven't really seen large trends. And that's sort of different. And I mentioned earlier, in sort of filtering down the data, we were specifically looking at human observed observations from pretty standard maritime or commercial ships. So of course there's a lot of other new observations from different kinds of data sources, different techniques for retrieving precipitation, but we wanted to focus on just this specific class, and at least there hasn't been a sort of big recent trend up or down as far as the frequency of those observations. So at least in that in particular, I haven't seen an area or a temporal range where we might expect some sort of influence from that.
But you did exclude the tuna fleet and you excluded the
Yep.
Russian ships, and they did have precisely the problem. They showed up in a burst like midway through the record, and were all over the place, and they kind of move around in blobs, chasing the tuna, I guess. And those did introduce various trends, and that's one of the reasons why they got floated out, because they weren't apparently reporting consistently with what other people in the area were doing. So it became more homogeneous after those were eliminated, and there was less of this variation in coverage. Is that correct?
Yeah.
Yeah.
I have two questions. First is kind of following the last question. Do you see any trends in just observations in general for polar climates with maybe technological advancements to ships to make them more confident to sail through areas of heavy sea ice? How does that play into the frozen precipitation records?
Yeah, I haven't looked too closely in sort of the relationship between, for example, like sea ice and where these ships are traversing. In general, I guess I could pull up the animation from Grant earlier, but in those, there hasn't really seemed to be too much of like a latitudinal change to where a lot of these particular ships are reporting observations. Though I guess for the Northern Hemisphere, these observations have been pretty consistent. I would caution some of these results that we're seeing in the Southern Ocean, just because pretty much the only time that ships are in this area are a very limited part of the year. And so some of these trends are going to reflect, like, we're not sure if these are actual, so for example, physical trends, or these are just related to just the frequency of sea ice. And actually, these observations down here, the tendency is related to just the frequency and the distribution of sea ice, actually. But whether that's a meteorological phenomenon that's causing these changes in frozen precipitation, or it's just ships are traversing areas that are previously untraversed. Southern Oceans is a bit sketchy for that one. But Northern Hemisphere seems more.
I have to cut it off, unfortunately, because I almost forgot that we have a faculty or departmental meeting in here now that we're already a little late in starting, so we'll have to, I guess, take further questions to the hallway for those who aren't in the meeting.